So welcome back everybody to Lahti Lake's 2021, the International Symposium on Lake Restoration Science. We hope that you enjoyed the first session this morning on food webs and biomanipulation. Thanks once again to all of the speakers, both the online presentation from Eric Jefferson and the three presentations that we had here in the studio from Finnish presenters. And thanks to all of you in the audience, the online participants who raised questions during the session. So just a couple of reminders, if anyone is joining us a bit later, that you're now viewing me in the main stage of the online platform. And this is where you can view all of the oral presentations, both the ones that are made from the studio and the ones that are made online by IFN support. And if you look on the left-hand side of the online platform, you can see that there are various rooms that you can also go to. The most important of these is, of course, the discussion room, which is where we go at the end of each of the oral sessions to continue the discussion on the topics raised in the session. Thanks to those of you who have participated already in the first of our chat online sessions. And thanks especially to our partner Mike Lurling in Wageningen in the Netherlands, who is chairing these discussion room sessions. And then also in this left panel you can find the abstract book, where you can find the full text of all of the abstracts of the meeting. And then we have, of course, the coffee room, where some of you joined yesterday for the icebreaker. The idea is this is a more informal hangout room if you want to just meet up with friends and discuss whatever topics come to mind. And then along the top panel, we have two tabs. One is the program and the other is the list of oral presenters. And then if we move to the right of the online platform, you can see the different chat options. And as we had this morning, please, I request that if there come up questions during the oral presentations, that you add these to the chat of the main stage. And then at the end of the presentation, I will be able to read what's been written and I will ask the questions directly to the speakers from here in the studio. But please also make use of the other functions. We have, for example, the possibility for a one-on-one video chat with any of the participants in case you wanted to continue the discussion. I should also say that in case you are watching the main stage during the breaks or during the lunchtime, you can see some beautiful pictures of our very own Lake Vesijärvi here in Lahti. So take the opportunity to look at this nice gallery of beautiful pictures. Okay, just before we start the second session, I will show quickly a few slides. So the topic of the second session is chemical methods in lake restoration, and specifically all of the presentations that we have in this session concern chemical techniques designed to inactivate phosphorus. So we're talking about in-lake techniques here. So this topic made the news in Finland shortly before the first Lahti Lake Symposium, when Lake Littoistenjärvi in the city of Turku was treated with polyaluminum chloride for the first time. And in the days following the treatment, the water in Littoistenjärvi became incredibly clear and the lake was briefly transformed into a popular holiday destination. And one of our first plenary speakers from the Lahti Lakes meeting in 2018, Jouko Sarvala, he was involved in the consultation leading to the treatment, and he spoke about the results in his plenary talk at the 2018 symposium. So in case you are interested to follow what has happened in the years since the first polyaluminum chloride treatment at Lake Littoistenjärvi, please visit Jouko's poster tomorrow in poster session 2. And as I said this morning, just as a reminder that all of the posters for both poster sessions are already there in the online platform, so you can visit the poster session at any time to look at the materials, and then in the schedule itself we have the two sessions when the authors will be in attendance to talk you through the content, where you can also ask questions and have a video discussion. So we're also hoping that Jouko Sarvala will be with us in this poster session, although the last we heard he was somewhere deep in the Finnish forest, possibly outside the internet connection. So we will see how it goes with him tomorrow. And as I mentioned this morning, please remember that we have a poster prize. So please visit the poster sessions, ask questions of the presenters, and consider that the ones also that make the best impression during the interaction might be worthy of your vote. Okay, so this was the end of my presentation for now. And now maybe we can have a look at the order of presentations in this session. So the session, Chemical Methods in Lake Restoration. It features 5 presentations in total, and the speakers will be joining us online from the Netherlands, from Germany, from Sweden, and from Canada. We start with an overview of the main groups of chemical activation methods for controlling internal phosphorus loading. This is given by Maira Mucchi of Wageningen University in the Netherlands. And that sets the stage nicely for the following talks, which each deal with specific cases of a certain type of chemical treatment. The second presentation is given by Brian Huser from the Swedish University of Agricultural Sciences in Uppsala, who will focus on aluminum-based methods such as those used in Lake Liitoistenjärvi. And then we have 2 presentations from PhD students working within the P-Trap Innovative Training Network, Carol Ass and Melanie Munch, who will speak about cases of iron-based inactivation. And then finally, Rao-Marie Couture from Laval University in Canada, who will speak about lanthanum-based treatments. So I think that Maira should already be online, so perhaps we can already move towards the first presentation. Maira, can you hear me over there in Holland?
Yeah, I can hear you.
Okay, great. So if you're ready to start, I would like to welcome you. Thanks very much for joining us. It's fantastic that you could present at Lahti Lakes again. We remember very well that you were here, of course, 3 years ago, and that was also an excellent presentation. And meantime, you published also in our special issue. Thanks very much for contributing to that.
Yeah, thank you for organizing.
So we're very excited that today you can give us this overview of chemical methods, in-lake methods for lake restoration. So please, Maira Mucchi.
Yeah, thank you. I am Maira Mucchi. I've been working at Wageningen University and also at LSI, which is a consultants company that focuses on lake restoration, specifically in tropical waters. And today I would like to talk a bit more about what kind of materials we have available to be used as a P binder, as a phosphorus binder. So to manage eutrophication in a successful way, the first step should be a system analysis. So it is important to know where our nutrients are coming from, if the sediment is the main source or the external source is the main pollution, and also to know what kind of organisms we have, specifically what type of fish and the fish biomass, and also to do a cost-benefit analysis. So this altogether will guide us to a set of actions that we could do. And it's important to highlight that more and more we see that not only one action would be enough, but combined of them. So earlier today, Eric gave a great example where fish was removed, macrophyte was planted, and a P binder was used to restore an urban lake. And I think through this symposium, we would have more and more examples where not only one action, but combined actions has been used. So in my talk, I would focus in P inactivation. So the use, not only the use, but also the research for materials that can inactivate phosphorus has been grow over time. So recently, I could find around more than 400 documents mention chemical inactivation of phosphorus in lake measurements. And when I look at closer in the last 4 years, I could find more than 100 materials that potentially can bind phosphorus. Most of them are modified materials, as the blue dots. Few of them waste materials, mainly for mining process, and a few of the naturals like soil, sand, or clays. So it's a lot of materials that potentially can bind phosphorus, but we can't use all of those materials because we don't know much about it, or they are not available in large quantities to be used in a large scale, for instance, a food application. And this is because before we used material, we need to know a lot of things about it. We need to know, of course, its efficiency in bind P, but also its efficiency under a realistic condition, for instance, pH range, redox, and also temperature, and also what kind of factors would interfere its efficiency. For instance, if we have other oxygens presence in the water, alkalinity, dissolved organic carbon, and also time itself. So for instance, there are few materials, that is aluminum and iron-based materials, that over time, they can crystallize and reduce their absorption capacity. So it is also important to keep in mind time itself. Another important point is safety. We don't want to solve one problem creating another one. So it is important to check what will be the consequence of those materials to non-target organisms, if it will be any release of compounds in the water, if pH will be affected or alkalinity, and how we can minimize that. And also there will be a range of ecotoxicological tests that needs to be done for each country because of legislation. Another important fact is the phosphorus desorption. So we check, okay, this material can absorb phosphorus, but if we change pH or if we reduce oxygen, what would happen? If this P will be desorbed again or not? And also important is the phosphorus fraction in the sediment, if this will change or not. For instance, we expect that those materials can actually reduce the phosphorus mobile in the sediment. So all of these tests needs to be done in different scales. So normally we start with tubes and flasks, where you can have a control of it, and also several replications to understand all the mechanisms and the conditions. Then we scale up to a more realistic conditions. And as you can imagine, this will take a lot of time and also investment. So it has been done some calculations in the past that until we develop the product and it goes through all these tests and actually can be used in large scale. And when I mean that it can be used in large scale, doesn't mean that we know everything about it, but at least that we know the basics of it. It normally costs 1 million euros. So then you can, and that is the main reason of all this time investments, that when we look at what kind of materials we have to be used as a P binder, is not a lot. It comes down for maybe 4 main groups based on the active ingredients, which is calcium. It's not very popular, but I will talk about it later. Iron compounds, aluminium, and recently lanthanum. So my idea here is to generally talk about them, giving advantage and disadvantage, but I will not go super deep on it because of time. And also I saw that we would have a few presentation case studies in aluminium, iron, and also lanthanum. So I think in the end, we would have a general idea of those products. So calcium can bind phosphorus through adsorption and also co-precipitation with calcite, for instance. But calcium-based materials haven't been that popular in the field of lake restoration because we only work at higher pH, so pH around 9, 9.5. So that means that we're not working out with the waters. Recently, there was a research that showed that calcite materials could actually reduce the P flux from the sediment. So as you can see here is a negative flux, but the dose was extremely high when you compare with normally dosed that has been used for other compounds such as aluminum, iron, or phoslock. So it's 1.5 kilograms per square meter. That's extremely high. So because of the pH dependence, and also it's less efficient compared to iron, aluminum, and lanthanum based, calcium has not been very used or not very popular nowadays. Iron, on the other hand, it's able to bind phosphorus under a wider pH range, but there is a negative point that it's commonly redox sensitive. So which means that once we have an oxidic event, most of the phosphorus that was before bound to iron will be released again to the water column. And as we know, that's occur quite often in eutrophic waters. So there are a few iron-based materials. So for instance, iron-rich sand that has been used. In the last years, I participated in a project, for instance, a mesocosm trial, where we add iron-rich sand together with aeration. So the idea of the project was that the system will not become anoxic because the aeration, and the ion present in the sand would actually be able to bind the phosphorus. So there are a few, we can always test that in a few conditions that ion-based materials would work. Recently, there have been a new product being tested. It's called CFH12, which is a dried iron hydroxide produced by a Finnish company. It have been used for water treatment. And recently, they also have tested if this material would be able to reduce the P-flux from the sediment. And they found that in 2 lakes at the test, so this one and this one, this compound was able to reduce the P-flux, but it's not a negative flux, as we can see. And there was also another compound, just iron hydroxide salt, that was able to reduce more the P-flux from the sediment. So it seems that it can work under a NOx condition because it reduced, but it would be interesting to test this for a longer period of time and also in stronger redox conditions to make sure that this product will also work in case we have a NOx event. Another recently ion-based material that have been tested by a Spanish group is the magnetic ion particles. So the idea is to add those particles in the system, but also maybe in inflows. And those particles would bind the phosphorus, and then you can actually harvest that to be used as a fertilizer in the future or something. And they also have tested these particles under a NOx condition. So this is phosphorus concentration over time, and the gray bars are anoxic period. And it seems to reduce phosphorus concentration, but the anoxic period was only 5 days. So again, it would also be interesting to exposure those particles to a longer period of anoxia, and maybe also a stronger redox condition just to make sure they were also able to cap the phosphorus. And also another product that had gained a bit of attention is to add iron 2 chloride in the segment to see if it would induce vivinite formation. In our group, together with Vetsus and Delft University and the water authorities from Brabant, we have tested this in the lab and also in the field experiment in the mesocosm. And we observed a phosphorus reduction in the water column, but we couldn't find the vivinite in the sediment. So it is still a project on the way. So we still need to change maybe a bit of the methodology, but we will keep working on it, and maybe next time we can present more the close results from it. So in general, the redox sensitivity of ion is viewed as the major negative point to use ion-based materials to manage eutrophication. There are a few new ion-based materials and new methodology, for instance, to try to induce vivinite formation. That seems promising, but still is in baby steps. That needs a lot to be done. And I saw that also today we would have 2 talks about ion-based materials, bring it to case study, so that also be interesting to see. And contrary to aluminum-based materials are not redox sensitive, so they would be able to bind phosphorus under NOx conditions. And aluminum is also able to bind phosphorus under a wider pH range compared to calcium. So that is also actually an advantage. So aluminum salts, once they are applied in the water, they will hydrolyze and they will form flocks. And those flocks actually are able to trap the phosphorus in the water column and also in the sediment. So aluminum will work between pH 6 and 8. If we have a pH lower than that, aluminum 3 would be the concentration of aluminum 3 will increase, and then it would have a toxic effect to the organisms and will not bind P. And if it's higher than 8, aluminate concentration will increase. That can also not bind P, and it can also be toxic for certain organisms. So it is really important to keep pH between 6 and 8. And aluminum salts, for instance, mainly aluminum sulfate together with sodium aluminate, and polyaluminum chloride have been widely used, mainly in the US, but also in certain countries in Europe. And we know a lot about it. So, for instance, in this symposium, we would have a talk right after my talk about aluminum treatment that I'm looking forward to it. And we also have a few posters about it. There is another aluminum compound, which is not well studied as aluminum salts. And it is a solid phosphorus phase, so which means it's not a liquid, but solid, which is Aqua P, is an aluminum modified zeolite and created by a company in Australia. And our group have been tested Aqua P under different pH, and it also seems to work fine. We saw a bit of variation, but that's also because of different batches of the product was used. We also test Aqua P in sediment cores, and we observed that Aqua P was able to reduce phosphorus from the sediment. And the Aqua P, because it's also a zeolite, can also absorb ammonium. So besides the phosphorus absorption capacity, can also reduce ammonium. And here I would like to highlight that it's well established that only one element is needed to reduce algae bloom and to manage eutrophication. And so far, we have been focused in phosphorus because it's easier and more feasible. But there are specific cases, for instance, when you have a high concentration of ammonium, that to apply zeolite, for instance, or the Aqua P can also be a tool to avoid ammonia intoxication. No? It's important to always have a tool in case we need. But for the Aqua P, it seems to work fine. But because it is more expensive than aluminum salts and also more expensive than another solid phosphorus phase, for instance, Phoslock, it is still not clear what would be the advantage to use it. So we are still looking at other possibilities and checking how Aqua P would work in a different water chemistry. So in general, aluminum salts are efficient in active P and have been widely used, mainly because it's not redox sensitive and work in a wider pH range compared to calcium-based materials. The Aqua P have gained attention, is not as well studied as aluminum salts, and have been, I think, a few applications, like a large field applications in Australia, but it's still not clear what would be the advantage, for instance, compared to aluminum salts or with Phoslock. Then we come to lanthanum. Lanthanum, similar as aluminium, is not redox sensitive, so which means that it would be able to bind phosphorus under anoxic events, and is also able to bind phosphorus under a wider pH range than calcium, but also than aluminium. So for aluminium was between pH 6 and 8. And lanthanum is able to precipitate phosphate under pH of 4 and 12. And once lanthanum is in contact with phosphate, it will form a stable mineral called rhabdophane. And this mineral will not, once it's formed, it will not be desorbed under natural conditions. And the most common lanthanum material being used is the lanthanum modified bentonite, commercially called as Phoslock. I think Eric also mentioned Phoslock in his talk, and we will have today as well a study case from Canada. So that will be also interesting to check Phoslock efficiency in a large scale. And another lanthanum-based product that have been developed, I don't think is actually commercially available, but we have been testing our lab, and there is also a Chinese group that have been published about it, is the lanthanum modified zeolite. So as you expect, because of the lanthanum, it will bind phosphorus, and because of the zeolite, we are also bind ammonium. But it's interesting to see that the natural zeolite would have higher ammonia absorption capacity than the modified one. So, and definitely, I think the natural zeolite would also be cheaper than a modified material. So it is also something to to keep in mind, and that a cost-benefit analysis in the end will guide us to what to be used and not be used. So in general, the lanthanum-modified bentonite is efficient and has been widely used. We'll have one example later today, and I think another case study from the Netherlands on Wednesday or Tuesday, not sure. And the lanthanum-modified zeolite have gained more attention in reduced phosphorus and ammonium, the same as the aqua P. They can absorb both, but still several tests need to be undertaken to understand this compound, to see also for metal release and so on. So it's not available in large scale as far as I know, or the literature shows. So the final remarks. There are several promising materials that can bind phosphorus. However, unfortunately, aluminum salts and lanthanum-modified are the most used one and the wide studied P binder. And that's mainly because they are able to bind phosphorus also under anoxic conditions and also works under a wider pH range. The chemical inactivation of phosphorus is extremely powerful tool against eutrophication, but it's not the magical solution. So there will be system that a P binder will not work or it will not be feasible. And this we can only assess through a system analysis. And also, the use of P binder should not be seen as an excuse to not reduce external phosphorus. Eric also mentioned earlier in his presentation about the importance to reduce external phosphorus, and that's indeed important. However, sometimes it's not visible, for instance, for diffuse source from agriculture, but also lack of infrastructure. And so to speed up the recovery, and here I'm talking mainly, for instance, if the drink water source is suffering from cyanobacteria bloom, there are several in-site interventions, for instance, P binder or biomanipulation that was discussed before, or then combined, that can apply to bring a relief to the system. And it's important to test those in-site interventions and also to share, as we are doing here, not only the successful stories, but also the negative ones. So then we can actually step forward to manage eutrophication and the cyanobacteria bloom. Okay, yes, thank you very much for your attention. I think I'm right time, yes.
Yes, thank you very much, Maira, for this excellent introduction to this topic. So while we're waiting for questions to come in on the online chat, I could maybe ask you, I thought it was fascinating to see that we now have some data for these zeolite-based methods that also are capable to sorb ammonium. So do you think that this is something that will become more common and widely used in the future, where we know that we're not just looking to control phosphorus, but we also have systems where there's a strong benefit to control ammonium?
Yeah, I think for certain cases that would be useful. So we have, for instance, a lagoon in Brazil that, besides the phosphorus problem, we also have ammonium, and that we saw that the zeolite could control ammonium from the water and also from the sediment. So I think that it's always nice to have different tools that can be applied for a specific case.
And a phrase that you used several times there was also this cost-benefit analysis. And of course, this is something that comes in from the side of water managers when deciding which approach to adopt, that some of the most advanced modern approaches might not yet be affordable. So how do you see the situation for, let's say, the development of this cost-benefit analysis in the future? Will it become more affordable to use these techniques, do you think? And are there, let's say, some kind of size thresholds in terms of the volume of a lake where it becomes impractical to consider certain types of materials?
Yeah, I think when we talk about costs, is always relative. So imagine, for instance, like in Rio recently, in Brazil, which is a big city of 8 million people, we had a drink, the reservoir was polluted and 8 million people were without water or water with geosmin. So when you think about, okay, it is a big system, a big reservoir, but then is it when you think that people don't have water to drink, then it becomes also a high, important problem that people need to invest on it. So it depends also. It's different when you have a lake that it's only for swimming or recreation activities, but when it's a drink water source, I think no matter the price, unfortunately, I think, you needed to invest in it because that would be maybe the only solution.
Okay, thank you very much, Maira. There have now come some questions in the chat, but I think the time is moving on. So please join us in the discussion room at the end of the session, and then you can answer to some of those additional questions. So thank you very much, Maira. And now we move on to the second talk of this session.